So good afternoon, everyone. This afternoon, we have a session on supernovae and BSM. We start with Jorge Martin Camalich from Instituto de Astrofísica de Canarias, which tells us about constraints on dark force. Please.
Okay. Yeah, so first of all, I want to thank the organizers for this opportunity and to talk about this work I have been quite excited about in the last year. And this kind of a likely connection, or apparently a likely connection between dark sectors and flavor physics and supernova. So let me then start motivating one of the two pieces that, of course, does not require much motivation with you guys, with us guys. So we know dark matter is one of the most prominent problems in fundamental physics at the moment. There's a huge effort to characterize theoretically all the possibilities and a huge experimental effort to actually search and scrutinize all these possibilities, right? And in particular, we have some very well motivated candidates such as WIMPs and axions that come from top-down constructions. But the fact that we have had null searches so far have shaken the community to try to think a little bit beyond and try to really look at the problem with a more open mind and maybe without theoretical prejudices or more agnostic, if you wish. This brings me to sort of one of these things that may fall into this category, that is dark sectors. Dark sector paradigm is something that we postulate exists that doesn't talk to the standard model except for gravity and hopefully some what we call portals. There are some particles like Higgs, neutrinos, axions, dark photons, which might talk to the both sectors and which allows us to actually test this hypothesis. Not only that, these portals are also interesting because we have many experiments searching and able to search for these particles because typically are maybe very light, ultralight actually, and this allows us to search for them in high intensity experimental infrastructures or experiments. Then let me bring to the other component of my title, flavor physics. You might remember what flavor physics is. It's nothing else than the fact that we know that the universe is made of something else than just electrons and nucleons. There are heavy quarks, heavier leptons, also neutrinos have three flavors. And as you know, flavor physics is per se and itself a very rich field. It's a huge phenomenology, very complex processes happening in the standard model. So we have current effort on understanding this picture of the CKM triangle, for instance. And also we like flavor physics because it addresses fundamental questions in the standard model, such as what is called the flavor puzzle, the hierarchies we see in the masses and CKM angles, relation, the fact that we have three families, baryogenesis, and so on, right? Now, what is the connection between flavor physics and dark sectors? Well, once you have a portal, nothing really tells you that the portal has to connect or to talk to us in a flavor universal way, or that just talks to electrons and nucleons that can have some more complicated structure and therefore, can induce some interesting flavor phenomena, right? There are one downside and one positive side to this possibility. I mean, it is not rare or strange that we have always aimed first to flavor diagonal, flavor blind interactions, just because it's simple. Also avoids proliferation of couplings, therefore it makes it falsifiable. Once you start including all these flavor transitions, then all that you are doing is just constraining different textures, if you wish, of your Lagrangian, right? However, I come back to the first question again. There is nothing at the moment, in principle, that prevents you to couple the portal and a non-trivial way to the flavor sector. Before I come to specific examples, let me say why this is motivation to do so, to try to think in this way. I will put you the main reason basically is that I think we're witnessing a golden era in flavor physics. There are two reasons for this. One is that we have built an amazing experimental infrastructure to actually test flavor physics at very different scales. from very low energies with electric dipole moments, lepton flavor violation, lepton EDMs, kaons, D mesons, B mesons, high PT, Higgs, top, etc. Right? So we have a lot of experiments which which brings a huge opportunity for discovery, not for constraining, but also for discovery if any of these realization scenarios are actually realized in nature. Within this also chapter of the golden era is the fact that we are actually, this is not hypothetical, we're actually witnessing the appearance, the emergence of some anomalies in data. In fact, there seems to be some laws in nature, some forces that like to talk to muons, but not to the other leptons. We have kind of two independent hints, I will call it, at least for me in G-2, but there's some piling amount of evidence that something is going on with B mesons decaying into strange on electrons or muons. It seems to be kind of a tension that is accumulating. And if you don't know yet already, there will be an announcement next Monday that have been announced today officially, a new result by LHCb that might contribute more to this picture right here. So we are increasingly being convinced that there's a systematic effect there. We still don't know if it's truly new physics or is a systematic effect that is spreading through all the analysis that these guys are doing. Okay, but this brings me again back to my topic of my talk. If I have these anomalies, and these anomalies are a portal to BSM, and BSM actually decides to manifest in this way, my question is, do these anomalies have anything to do with dark matter, baryogenesis, and so on, right? So this is an extra motivation for me actually to try to, to connect these two things just in case this turns out to be true. And in that case, maybe all of this is connected in some way. Let me come then to specific examples where actually we know the dark sector, dark portal can be flavored. The first prime example is the axion. Maybe the first idea in that direction will be the familon or axiflavon of Wilczek, where he tries to solve and address the flavor puzzle and strong CP problem at the same time by spontaneously breaking some horizontal symmetry. And this brings naturally, an axion that also couples non-trivially to flavor. In general, you can also construct DFSZ type models, which do not have universal couplings charges to the standard model fermions. This automatically makes you sensitive to the rotation unitary flavor matrices, right? Again, the possibility of having flavor violation in the axion couplings to the standard model. Last but not least, the axion itself, even if you start with flavor universal couplings to the fermions, the standard model per se, running at the loop level, relative corrections give you flavor violation when you run all the way down, all the way from the pitch queen breaking scale all the way down to our electroweak scale or low energy scale. And this is also something that is interesting. The second example I will mention is dark baryons. So what dark baryons are dark particles which are charged under the baryon number. Then you make them typically heavier than proton, so you kinematically block proton decay. And there have been interest in this type of scenarios very recently on the theoretical side because they are predicted as a byproduct of a solution to baryogenesis and to predict the dark matter relic abundance through the so-called B mesogenesis mechanism. If you don't know about this, there are a few papers starting by, I think there were some precursors, but I think the first paper is this paper by Elor, Escudero, and Nelson 2 years ago. Essentially, you make heavy scalar decay out of equilibrium into B bar pairs at basically at 10 to 20 MeV or so, a low energy baryogenesis. These B and B pairs immediately hadronize into B mesons, and the neutron B mesons start to oscillate in a way that breaks CP violation, right? So you already get out of equilibrium, CP violation. The last thing that you need is something that at least seems to break baryon number. The way to do this is to introduce some coupling of these quarks into dark sector that carry baryon numbers. So you will have signatures like B going to a baryon and to anti-baryonic dark sector particles. Now, when you put all these pieces together, what happens is you produce homogeneously, symmetrically, then these oscillations break the CP symmetry, and in the meantime, they start decaying to these things, accumulating an abundance of baryons in the visible sector and antibaryons in the dark sector, producing at the same time the baryon abundance and the anti-dark or the dark matter relic abundance. Okay, so this is in a nutshell the mechanism. Is also it's interesting that it produces baryogenesis with the standard model CP violation, so you don't need any exotic source of CP violation. That's interesting. Of course, you have a new source of particles, dark sector particles. On the other hand, give you that matter. Okay, what is good about this framework is that it's testable because you predict things like P decays going to lambda and invisible. So signatures that seem like baryon number violation. Another motivation for this is so-called the neutron lifetime anomaly. This is another anomaly of flavor physics or nuclear physics, if you wish, which I don't think is at the same level as the ones that I showed you earlier, because it's not really clear that the two experiments are completely, the systematics completely under control. But I tell you what the anomaly is. So you can measure the lifetime of the neutron in two different ways. One, in accelerator physics, you produce neutrons and you look for the decays by searching for the electrons and protons in the final states. So you count, you know the flux, you count the number of protons and electrons, and you can calculate in this way the lifetime, because you do count an experiment. In the bottle, on the other hand, you put a lot of neutrons in the bottle, you count the number of neutrons at some time, you count the neutrons at the second time, and this allows you to measure again the lifetime of the neutron. And what happens is that the two measurements differ by or different by 4 sigma almost. If you see the one of the beam, the lifetime is slightly larger, the one of the bottle is slightly shorter, and people have interpreted this as if the neutrons in the bottle are decaying through dark channels, because in the bottle you don't see any decay products, so you don't care. Whereas in the beam you're actually measuring the standard model decays. So that's the reason why you will see different branching fractions. And the signatures are again of the type neutron to invisible and a photon or infrared photon or pure invisible decays of the neutron. Okay, so these are two scenarios that encompass this dark baryon sector. The last example I will mention is the dark photon. When the dark photon is massless, you can always rotate away one of the two fields in such a way that the actual photon only talks to the standard model, in such that the dark photon doesn't talk to us. Therefore, that means that the dark photon, the massless dark photon, is such that does not interact with us with a normalizable interaction. But still, you can construct some higher dimensional operators, which you can easily UV complete. And in this UV completion, it's almost natural to get flavor violation. Also, it's very difficult to test this because it doesn't interact with at the normalizable level. So you need to resort to this type of scenario, to this type of searches to actually probe into this possibility. All right, this is just 3 examples I just have been working interested in recently. There's currently a effort in the SNOWMASS efforts and the SNOWMASS document now, gathering more than 50 people trying to scan all the theoretical possibilities and the corresponding searches that we can do in our current flavor facilities. This is just an example of what you can do at the moment with the QCD axion paper I published with these people, where you basically take all the possible decay channels, K to pi A, B to pi A, you try to do what can be measured, probing, and like an EFT, being completely agnostic about the structure. You can do beautiful calculations in the EFT, in QCD, chiral perturbation theory, and so on. You incorporate RGEs and you put all together in a beautiful plot that will show towards the end. And the thing that I mentioned this is because one of the things that pop up in our discussions, but in particular with Maxim Pospelov, that is the one that basically gave rise to this idea on a Blackboard discussion at CERN, was the fact that if we have something like lambda to neutron axion, then you will get a supernova bound. You can recast the traditional supernova bound on axion emission, cooling emission through this type of decays. And this is what I'm going to discuss today. So this brings me then to supernova. I mean, I'm not an expert on this. I just reproduce what I learned in the textbook. The mechanism, we know that is the fate of massive stars that happen when we have burned all the fuel and we have reached a situation in which our core is made of iron that cannot fuse in order to produce more energy at some point, and the core, of course, is sustained against collapse due to the pressure of the degenerate electrons. At some point, the temperature becomes so high that you start basically photodissociating nuclei, the iron nuclei, and neutronizing the star, emitting neutrinos. This reduces the electron pressure, making the core, the mass of the core to be above the Chandrasekhar limit. Then you trigger collapse. And in triggering collapse, basically you start photodissociating all the core, neutronizing all the core, and radiating even more neutrino, accelerating the process until the point you reach nuclear densities at the core. At some point you get a situation in which your the matter content of your core is basically neutrons, and they are become degenerate, stiffens the equation of state. So this stops collapse, and all the surrounding material stops and bounces. And this in principle should start triggering the explosion. Now, at this point, what I'm interested in is what remains in the center. It's a proton neutron star. Neutron star that is very hot. The heat produced by the collapse itself, and this radiating neutrinos like crazy. So at the same time, the envelope is expanding due to the shock, photodissociating and losing energy in the process, while it accretes more mass to the center. There is accumulating neutrinos, the prompt neutrino bars, and so on. But what is important, and maybe also there will be discussion, is whether this explodes at the end or not. And it's believed that all the neutrinos that are being produced from the core will eventually deposit their energy while they diffuse in the mantle and will eventually make the star explode. So I'm interested in this situation where we believe there exists a proton neutron star in the core, and this is emitting through the emission of the neutrinos. This is the only way that actually the supernova can cool itself, because nothing else can escape. But in principle, if all neutrinos there is all there are, then it means that it can only cool down, it can only radiate a neutrino for a big part of the evolution, and that means that 99% of the emission of the energy, gravitational energy lost through collapse, is radiated or emitted in terms of neutrinos. So this is one prediction of this mechanism. Another prediction is that the average of energy of the neutrinos have to tell you about the temperature of the core. So basically, you are predicting that the spectrum should more or less be of the order of tens of MeV. And another thing is the time scale of the cooling of the neutron star that you know from simulations that should be of the order of 10 seconds. Okay, so these are the main observables you'd like to test or to check with an actual supernova happening close to this. And this has happened in February 24, 1987. Supergiant at the Large Magellanic Cloud, 50 kiloparsec exploded. And actually, we were able to see what we believe is the burst and the emission of neutrinos during this supernova, measured by these three different experiments, organized in time and in energy. And you said that more or less follow what you would expect from what we knew from supernova simulation at the time. Also, there is some indications, recent indication, maybe we will discuss later about this, of the possible existence of a neutron star at the core of the supernova remnant that might indicate that indeed this was a core collapse supernova. So all observations seem to be consistent with core collapse theory. And of course, how can you use that for our purposes? Well, this is the classic argument. When you now turn on some dark channel, dark mechanism by which the supernova can cool itself, like neutron, nucleon, axion coupling, then you will start radiate axions like crazy with this type of mechanism. And you can see what is the main effect that this will create in your supernova evolution. And you can see that the main effect is shortening the duration of the neutrino pulse. And this is a beautiful plot that you can find in Raphael's, Jorge Raphael's book, where you basically see what will be the time, the duration of the time, or the some convention that you define it, and then you see how it depends as soon as you turn on the Yukawa coupling of the axions, and you see that while you increase, you basically shorten dramatically the duration of the pulse all the way down to 2 seconds, okay? And at some point, you make the coupling so large that the axions do not escape the star any longer, so they get trapped, and then you get back to where you were, okay? So this is the basic plot. And then this tells you that you can basically put a constraint from the fact that we are observing neutrinos over 10 seconds from supernova 1987. And this can be all summarized and compactly put down into a criterion that's called Raphael's criterion. And apparently, Jorge himself doesn't like this criterion to be called Raphael's criterion. But anyways, this is the criterion, and what you have to do in order to apply all this knowledge into bound is basically to ask your dark luminosity. If you have a dark particle, your dark luminosity have to be smaller than the neutrino luminosity at one, and the criterion is to put this at 1 second post bounds. Okay. Now, this is what is effectively used to set bounds on that cooling. We will have a discussion later, very interesting. I just want to say, of course, I'm outside to all these technicalities of the how supernova work. I just want to say also to point to Thomas Janka's colloquium at CERN was really interesting. As an outsider, I see they are at the level where they are testing the simulations, with many astrophysical observables of the sort of nucleosynthesis, these kicks and particular velocities of neutron stars. And, from an outside point of view, of course, there are many details, and the devil hides in the details sometimes. But, it seems convincing that the whole picture works. Of course, we will hear more later about this, but this is the only thing I wanted to say at this point. Okay, so I'm gonna buy the core collapse supernova scenario, and then this brings me to, okay, what hyperons have to do at all with supernova, neutron stars, and so on. And the point is that the supernuclear density, you get a large baryon chemical potential, and there are two ways where you can think that the hyperons naturally start populating the proton-neutron star. The first one is temperature. You have first of all, what are hyperons? Because maybe you are not familiar with this, completely familiar. Hyperons are just the strange siblings of the proton and the neutron. So if you start replacing U and D quarks by the strange quarks, you will basically fill out the what is called the baryon octet. So since the strange quark is heavier than the U and D quark, you will get heavier siblings. For instance, you have the so-called lambda particle that is 1.115 GeV. Therefore, you see the mass splitting is the order of 175 MeV, and for temperature of the order of 15 MeV, it's not hard to imagine that thermal fluctuations will create a thermal population of lambdas, and you can estimate this with a Boltzmann factor, and you predict of the order of 1% of lambdas as compared to neutrons, right? So you have lambdas in principle thermally produced in the supernova. The other process that you can imagine is when you reach nuclear densities, you start filling the Fermi sea, even in the T equals 0, you start filling the Fermi sea, and at some point, the energy that you require to put more neutrons in the Fermi sea is larger than the mass difference between the proton and the lambda, and then it becomes energetically favorable to start filling the lambda sea instead of neutron sea, okay? And this is, of course, well known in nuclear physics, in all this equation of state people. At some point, you reach a density, you start populating all these states just because of density effects. Okay. Right. So now, what does it mean? I have lambdas in my neutron star. I have lambdas in my proton-neutron star. So as soon as I connect some dark decay channel, this will produce and contribute to the dark luminosity of the star. So this is basically what we did. We calculated the emissivity. That means the energy that we radiate per unit volume, unit time, as a function of the spectrum of the energy. It's a simple formula. The only two elements I want to highlight are basically, well, you need to predict sort of the distribution functions of lambdas and neutrons inside of the star. And the second thing is I can express everything in terms of the decay rate of this process in vacuum. At this point, I don't need to specify anything at all about the microscopic structure that is giving me rise to gamma. Gamma is completely model independent function that only depends on the quantum numbers of final state, scalar or a boson, and that's it. Okay. So eventually, the fact that they have gamma here means that I will put a model independent bound from supernova on a branching fraction of lambda to neutron invisible. This is a sort of a simple formula, but it can be made even simpler by taking non-relativistic limit, and it looks like this. This is Q once I integrate in omega, and basically it's the number density of lambdas, mass difference, and gamma. That's it. Super simple. Of course, we will use different formulas to check, the different approximations, but that's how it looks. Of course, one has to take into account reabsorbing and trapping, because at some point the coupling can be so large that the X0 that you radiate can go back to lambdas in the plasma, right? And this is a known procedure how to do this. You calculate the mean free path, and there are two ways you can estimate this. One is by calculating the dark luminosity with a damping factor that has to do with the optical depth. And the second way that is more general, is more brutal, is the extreme, where you assume that the axions or the particles have thermalized, and they define the same way like a photosphere, neutrosphere, a dark sphere, which is basically the one from where the optical depth is basically 0 or small, right? And then what you have is black body radiation with the corresponding temperature, and that's it. Okay, so this is all the analytics. Of course, you need to put some things. You need to predict this decay amplitude. Distribution functions that depends on the properties and the equation of state and so on. So you need simulations and you need an equation of state. The simulations are done by Janka's group, 1D simulations that are artificially triggered. I will also mention something about why about these simulations later on, because they were devised to put bounds on a different thing, on a different animal. There are two equations of state. These are predictions of density and temperature that are radial profiles that we use in our calculations. There is a subtlety, though, is that in their simulations, the equation of state did not include hyperons. So we have hyperons. So in principle, is not consistent. However, equations of state are currently produced sometimes in higher degrees of complexity. So you start with an equation of state that doesn't have hyperons. And of course, at some point, you put hyperons on top because you know that they become important at certain densities and temperatures. And the point is that these two, with and without hyperons, are calibrated with each other at low temperatures and low densities. And the point is, especially low density, and the point is that for the proto-neutron star, the densities that you reach at the core are not super huge compared to neutron stars. And you can compare the thermodynamical properties, pressure, free energy, that one and the other equation of state give you for all the conditions of interest reached in the supernova and proto-neutron star, and you find that they are basically analogous with each other. The discrepancy and the difference between them is a few percent. So at the level of simulations, it does not matter whether I use the one with hyperons or not with hyperons, because I don't reach the conditions where this difference becomes sizable. So another thing, comparing to equation of state, SFH and LS220, just to mention that LS220 is not consistent with two solar mass neutron stars, so it's not kosher. So we will basically show results for that, but we will focus on SFHO, which is consistent, is among the few hyperonic equation of states which are consistent with these observations. Okay, so this is basically how it works in practice. This is the abundance of lambdas that we predict as a radii for the different simulations. Just one feature I want to show is the fact that hyperons disappear basically at 10 kilometers. This will be important for the reason I will mention in the next slide. And that you can also incorporate microscopic information. I mean, once you have lambdas in the medium, you have to take into account that the masses, the of these lambdas change, the dispersion relation of the lambdas in the medium and the neutrons change. This is usually parameterized by effective masses you might have heard of, and also by vector potential. It's a model-dependent way of trying to see what happens with the particles in a high dense and high temperature medium as the one in the neutron star, okay? So we incorporate this. You need to incorporate this at least to get the abundances, but you can also incorporate this in the level of the calculations you're doing because it's changing completely the energetics of your process. So we have also incorporated this in a way. So these are different.
Jorge, sorry,
Yep.
what were the 3 lines on the plot?
Yeah. So these are the abundances. Okay, so there are 3 lines. There are actually 5 lines. So this is one, the so-called LS220. This is the equation of state, one of the equations with the corresponding simulation, which this is the one that does not, this equation of state does not produce, is not rule out, but is quite disfavored by the fact that it does not produce 2 solar mass neutron stars. Then this is the spread of SFHO, where this is one of the calculations, and this is the other 2, with where the difference lies. I mean, the same equation of state, but the difference is I forgot to mention this. The simulations have different neutron star remnants. This is the basic uncertainty that we have at the moment on how heavy the remnant neutron star mass might be. Okay, so we have one with this equation of state, one with this equation of state, but with 3 different neutron star masses. So these are the 3 lines, the band here. And last but not least, I put just what I will get from a Boltzmannian factor, just assuming neglecting all equation of state, only thermal produced. So this is the most general, more model independent thing you can do. So even in that case, you predict an abundance thermally produced of lambdas, just to have a. Okay, so these are, well, these are the predictions or the bounds in terms of a branching fraction 10 times to the 10 branching fraction for the different simulations, different approaches. This is the most sophisticated one that incorporates all the effects. So this is the one that we want to take. And across all of this, this is the most conservative. So you see that if you change equation of state, doesn't change much. If you change approach, doesn't change much. But if you change the mass of the neutron star remnant, it changes by an order of magnitude, okay? So we take the most conservative one. This is an observation. Trapping is not an issue for us. The reason is because lambdas disappear in a very hot region of neutron star. So this sets the maximum radius of the dark sphere, meaning that if you calculate the luminosity there is huge, many orders of magnitude above the Raphael's criterion, the luminosity of neutrinos. And then this leads us to this model independent branching fraction on lambda to neutron invisible. 5, 10 to minus 9, which is very, very large, as I will show, very, very, very stringent, as I will show. This is basically a plot where you change, similar to all these plots I have shown, for different simulations, and you see where basically it crosses the. So let me then furnish this gamma with different models. Let me start with the axion. And then this is the rate, which depends on the parametric in the microscopic couplings, the Lagrangian, the CBCAs, some form factors, QCD form factors I can get from lattice, data, and so on. And this is the typical plot you get. This is the paper I mentioned earlier where we did a complete scan of the phenomenology of the flavored axion. And you see these are the 2 couplings I'm interested in because they are transitions, mediated transitions from S quark to D quark, where you see this is the usual and the famous K plus to pion axion. And we see that the bounds of this one is vectorial, this axial vectorial. So this setup on the axial vectorial. The supernova is the strongest bound on the axial couplings of the axion to this current. Of course, you need you need something that only talks axially, which is kind of fine-tuned, because of course this vectorial bound is order of magnitude stronger. Okay. Of course, there is some caveat with respect to the axion when you start, thinking of an ALP when you give a mass, because these searches, experimental searchers, have a gap in the sensitivity due to K2 pi region, to K2 pi background. So any ALP here will be basically you almost not blind because you lose many orders of magnitude. But here is where the supernova bound will probably make an impact. If I move to massless dark photon, in this case, you don't have K2 pi photon because of angular momentum. So you have basically now this tensor and these couplings. And as a matter of fact, the bound from supernova is the strongest bound overall in the quark sector and is more or less competitive with the one from star cooling and electrons in the lepton sector. So, you know, this is baryon sector. Dark baryon sector is something that we are currently working on. This list of authors here. This is the type of mechanism that you will have. Here is something that contains a new component, and it's the fact that these guys are typically heavy, so they are non-relativistic, and therefore that means that most of them will get gravitationally trapped inside of the neutron star. They will create some basin in a sense. And then you have to take this into account, because then you know this is part of the flux of the spectrum that will not contribute to the cooling bound, right? So we did basically we cut out all the energies that were not large enough to let the particles escape, and this means that in many of the channels we get reductions on the bounds of a few orders of magnitude. Okay. But still, they can be as strong as 10 to the minus 9. And to let you know how relevant or timely this is, today there was a result by Bethry, precisely on branching fraction of lambda to invisible, where they measured 7.4 10 to the minus 5, basically 4 orders of magnitude below or less stronger or you know, weaker than the bound that we get from supernova. Okay, last but not least, there are muons. Muons are also in supernova. Actually, this was before us. We were inspired by this paper. Bolig and collaborators, they did the same, you know, completely different physics, but essentially they put best limit of couplings of the axion to muons. And there was a follow-up by Kroon and collaborators where they did the same with C primes. So you already did in C primes, and the point is that you can put constraints on very heavy and relatively heavy C primes. And what I find is interesting is that you will constrain parameter space of C primes that are well motivated by flavor anomalies. And the example is this paper by Almanzov and all. This is a classic paper where they use a gauged U1 tau minus mu. And in fact, this can be very light, and the lighter part of the spectrum could be constrained by this type of argument. Okay, with this, I reach my conclusions. I think my 3 messages is that there's an increasing interest on dark flavor sectors. 2 reasons: because there are powerful experiments probing this type of sectors, and on the other hand, there are flavor anomalies that prompt us to question and to try to connect the possible BSM extensions that we need for this with problems like dark matter and baryogenesis. The second message is that once you allow and you think and you you have these dark flavor sectors, then there is a supernova bound on these sectors. And the basic 2 ideas that heavy flavors are at thermal equilibrium, existing thermal equilibrium in the proton neutron star plasma, and dark flavor sectors will cool the proton neutron star. Finally, the supernova is very strong and may help guiding future searches, as I illustrated with the invisible decay of the lambda. Okay, thank you.
Hello, Jorge. Questions? So I asked the first one, why Hyperons and not other baryons in addition to, I mean, have you tried if there is any constraint power by considering?
No, the problem is the mass splitting, right? Hyperons are all these strange baryons, so you have this multiplet, but the point is that any heavy baryon with charms will be GV heavier.
No, yeah, but like, I don't know, anything else than neutrons, anything else? I mean, this is a very naive question. Like,
you mean like sigmas? Or,
yeah.
Yeah. You could have them. And in fact, there's some, but for example, the sigma, the one that you will get is sigma minus, because it will allow to reduce the chemical potential of electrons, the Fermi, because it's negatively charged. And then the sigma minus does not decay. There's no proton without, there's no nucleon without the strange as a negative charge and baryon, the same baryon number as, so you don't have sigma minus decay into anything. You can have sigma minus decay into pi minus and invisible. This we have done, but we have not implemented in the calculations yet because it's a little more tricky at the level of the models and so on. Yeah.
But you did. Okay.
Well, we guessed,
okay.
But you see different equation of state. It's not that easy to get from a conclusion. While and it's not clear it's much larger than the lambda. So.
Okay, thanks. Questions or comments?
Hey, so in the previous slide, for the case of mu minus tau,
Yep.
F bound from cosmology, I would guess that anyway below 1 MeV should be anyway excluded, no?
Well, I don't know. Maybe they have some n effective here, but
I see. Yeah, that's it. Okay. Yeah, because I guess that, you know, if I mean anything that is below 1 MeV and very strongly coupled will mess up with cosmology, you know? So
right.
that will be excluded anyway, even without supernova, if you're like
Yeah.
Yeah.
I agree. Yeah.
Okay.
Other questions? If not, we thank Jorge again.